Very good morning, student. This is Dr. Sumanta Rakshit, Associate Professor of Civil Engineering Department at Haldia Institute of Technology. Now, today I would like to discuss on topic hydraulic conductivity of soil. This is the overview of my today's lecture. First, brief introduction, then importance of hydraulic conductivity, Darcy's law, factor affecting hydraulic conductivity of soil, and last, how we can find the coefficient of hydraulic conductivity through laboratory testing. What is hydraulic conductivity? It is nothing but a measure of how easily a fluid, here I am talking about water, can pass through a porous media. Here porous media means soils. In other words, you can say hydraulic conductivity is the property of soil through which water can flow through its interconnected voids. Okay. Hydraulic conductivity also known as permeability of soil. So don't be confused. Now you can see here there are two figures. Left one is one loose soil, right one is one dense soil. In case of dense soil, you can see, in case of loose soil, you can see the voids is more and voids are interconnected. So through loose soil water can flow easily and permeability will be high. But in case of dense soil, as voids is less and voids are not interconnected, due to this water cannot flow easily and permeability will be less. The importance of hydraulic conductivity. Hydraulic conductivity play a major role for design of earthen dam, stability of slope, retaining structure, and also for design of filter, and as well as the estimating the quantity of underground seepage. Flow of water through soil. When water flow through a soil, the flow may be laminar or turbulent. Okay. Now, in case of laminar flow, the fluid particle travel along a defined path which never crosses the path of any other particle. But in case of turbulent flow, you can see here the paths are irregular and twisting in nature. Darcy's law. Now you can see the figure. There is a saturated soil system which is marked here in yellow color, whose cross sectional area is capital A and length is L, and at the inlet and outlet there are two piezometric tubes inserted and water is filled at inlet piezometric tube, and initial head that is equal to H1 and final head is equal to H2, and del H is the head difference. As now we know the hydraulic gradient I, that is I is equal to head loss, that is del H, divided by length of flow path. Here length of flow path is L, capital L. Okay, so as per Darcy's law, in a saturated soil system under laminar flow condition, rate of flow of water is directly proportional to the hydraulic gradient. That means if V is the rate of flow of water, so we can say as per Darcy's law, V is proportional to I and V is equal to Ki. Here K is the coefficient of permeability. The unit of permeability, that is meter per second or centimeter per second, whatever you can say. The following are the assumptions of Darcy's law. First assumption is the soil should be fully saturated and temperature during testing is 27 degrees centigrade, and flow through soil should be laminar and entire cross-sectional area is available for flow. Coming to the discharge velocity and seepage velocity. Now, discharge velocity is defined as the discharge per unit cross-section area of soil. If V is the discharge velocity and Q is the discharge per unit time and A is the total cross-sectional area of the soil sample, so we can say V equal to Q by A. Okay. But in case of seepage velocity, it is defined as the discharge per unit cross-section area of voids. If Q is the discharge per unit time and AS is the area of voids, so we can say seepage velocity Vs is equal to Q by AS. Now, what is the difference between seepage velocity and discharge velocity? In the case of discharge velocity, what happened? The total cross-sectional area of the soil is considered, but in case of seepage velocity, the cross-sectional area of voids is considered. Okay. So there is a relation between seepage velocity and discharge velocity. That is Vs is equal to V by N. What is N? N is the porosity of the soil. As we know, porosity of the soil is less than 1. So as per that relation, we can say the seepage velocity always greater than discharge velocity. Following are the factors which affect the permeability of soil. First one is the particle size, then void ratio of soil, properties of pore water, degree of saturation, presence of entrapped air, structural arrangement, stratification of soil. Now coming to the particle size. Permeability varies approximately as square of diameter of the soil, as K proportional to d substance square. d10 is the effective particle size. Now we can see the figure. At the bottom there is a clay particle, above clay there is a silt, and at the top there is a gravel, and below the gravel there is a sand. So as the particle size increases, then permeability also increase. Void ratio of soil. If the presence of voids is more, then permeability is also more. There is a relation K proportional to EQ divided by 1 plus E. Here is the void ratio, K is the coefficient of permeability. And there is another relation K proportional to E square. But this experimental verification failed to justify any of this recommendation to be uniformly applicable to all type of soil. Okay. Paradoxically, for clay soil, void ratio is more than other soil. But what happened? But as per above relation, for clay soil, permeability will be more. But practically, this is not happen, because in case of clay soil, voids are not interconnected. That's why for clay soil, voids is more, but permeability is less. Okay. The property of pore water. Various properties of water also affect the permeability of soil, like unit weight of water, viscosity. Okay. Now, unit weight of water will not affect much, since it does not change much with temperature. But with temperature increases, the viscosity decreases rapidly. As a result, permeability increased. Degree of saturation. Higher degree of saturation also affect the permeability of soil. Soil should be fully saturated or partially saturated. In case of partially saturated soil, voids of the soil occupied by air and water. But in case of fully saturated, voids of the soil occupied by only water. So in case of partially saturated soil, as air presence, this air basically block the flow path, which reduce the permeability. So as a result, so for fully saturated soil, permeability will be more than the partially saturated soil. Presence of entrapped air, as I already discussed in previous slide, as if air presence within the soil mass, then what happens? Which block the flow path of the water. As a result, permeability will be reduced. Structural arrangement. Now we can see here there are two similar type of soil at same void ratio, but permeability is less because of their structural arrangement. In case of there are two figures. At the top there is the flocculated structure, at the bottom there is a dispersed structure. Now in case of flocculated structure, what happened? Soil particles are in random orientation and permeability is more in this case. But in case of dispersed structure, particles are face to face orientation. As a result, permeability is less. Another important thing is that for a stratified soil deposit also affect the permeability of soil. Stratified soil deposit means the multiple number of soil exist. If flow is parallel to the soil bed, then permeability will be more, and if the flow is perpendicular to the soil bed, then permeability will be less. The laboratory testing to find the coefficient of permeability. Now there are two methods to find the coefficient of permeability through laboratory testing. One is the constant head permeability test, another one is the falling head permeability test. Now coming to the constant head permeability test. Constant head permeability test basically performed for coarse grain soil. What is coarse grain soil and what is fine grain soil, that I have already discussed in previous classes, so I will not discuss too much. Okay. Now we can see the figure. There is a soil which is compacted within a mold. The length is the L, and total cross sectional area of soil is capital A. At the bottom and top there is a porous stone. Okay, and at the top there is a tap to supply water throughout the experiment, and the bottom there is an outlet to collect the water at a regular time interval, and the H is the head difference which is constant throughout the experiment. So as per Darcy's law, we can derive a formula to find the coefficient of permeability, that is K is equal to QL divided by ATA. Suppose Q is the total volume of water collected at a time T. Okay, and L is the length of the soil sample, and capital A is the total cross sectional area of the soil, and H is the head difference. So we can find out the K is equal to QL divided by ATH. Now coming to the falling head permeability test. Falling head permeability test basically performed for highly impervious soil, that's mean fine grained soil. Now we can see here a soil sample compacted in a mold. The cross sectional area of the soil is capital A and length is L, and at the top of the soil a standpipe is connected and cross sectional area of the standpipe is small a. At the bottom there is an outlet to collect the water at a regular time interval. Suppose at time t is equal to 0 and water is filled in the standpipe, and at a certain time t the water is dropped down. Suppose final head that is equal to H2 and initial head that is equal to H1. Okay, so by applying the Darcy's law, Darcy formula, we can derive the formula to find the coefficient of permeability, that is K is equal to 2.303 AL divided by AT into log 10 base H1 by H2. Here small a is the cross sectional area of the standpipe and capital is the cross sectional area of the soil sample, and T is the time duration, H1 is the initial head and H2 is the final head. Okay, and L is the length of the soil. Now for better understanding, solve a numerical, that is the permeability test is carried out on a clay soil having cross sectional area of 60 square centimeter and height of 15 centimeter. The water level in the standpipe of diameter of 0.5 centimeter drops from 100 centimeter to 40 centimeter in half an hour. What is the coefficient of permeability? Now from this figure, which formula you have to apply? That is actually here what there is a head is variable. That means you have to apply the formula for falling head permeability test. Okay, now see the figure. What is the data given? The total cross sectional area of the soil is given, that is A is equal to 60 square centimeter. Height of the soil, that is L is equal to 15 centimeter. Okay, and the dia of the standpipe is given, that is 0.5 centimeter. You have to find out the cross sectional area of the standpipe, that is small a, you have to find out. Okay, and initial head of the that is 100 centimeter and final head that is equal to 40 centimeter, and time t is equal to half an hour, you have to convert into second. Okay, now see data given is given already. A is equal to 60 centimeter square, L 15 centimeter. You have to find out the cross sectional area of the standpipe, that is A is equal to pi by 4 into 0.5 square, that you can get the result, that is equal to 0.196 centimeter square. Okay, and convert the time into second, that is 30 minutes, 30 into 60 second, that's 1800 second. Now put the value in K is equal to 2.303 AL by 18 to log 10 base H1 by H2. Thus you will get the permeability, that is 2.49 into 10 to the power minus 5 centimeter per second. Okay, here H1 is equal to 100 H1 is equal to 100 centimeter, H2 is equal to 40 centimeter, and cross sectional area of the standpipe, that is 0.196, and cross sectional area of the soil sample, that is equal to 60, that is already given. Just put the value and you get the result, that is k is equal to 2.49 into 10 to the power minus 5 centimeter per second. Okay, thank you.